Thank you and welcome to this talk. I thank the organizer for being so nice to invite me, to give me the opportunity to show some of my work here. So I'm going to talk about a piece of 3D deep learning, which is a combination of reconstruction and synthesis. So an image or a video gets into a deep net, which should get a whole scene 3D reconstruction. We want to recognize objects belonging to certain categories, recognize their shape in the images, also resolving interactions between objects. Like here, the table is occluding the chair, and you want to reconstruct also the part of the chair that's behind the table. Or here, the bottle is supported by the table, and it's the kind of analysis you should be able of doing. So in the end, you want all the objects into a single common coordinate frame, consistent. Then the other side of the story is that you want to be able to change the camera and draw an image of the scene from any other viewpoint. And why stop at that? Maybe you want to change a light, write your name on the table, make the bottle opaque instead of transparent. Any kind of edits from a single image would be great. So if we could do this, we could do a lot of applications. One of them is interactive media. For example, if you want to change the texture of that chair, you will need to understand its 3D shape. Otherwise, the shading on the texture will not look right. Augmented reality, we heard it a few times today. It's very important to place virtual objects in the real world. You need to have a degree of understanding of the scene. Autonomous driving, like Alex was talking a bit about, also requires understanding 3D scene, and also understanding what people do in a space requires that too. So here is before deep learning, which wasn't so long ago. I like that Georgia said, when she started, there was no deep learning. I started another 10 years before that, and actually deep learning existed. There's no other name, and it was associated with failures. Nobody wanted to be associated with deep learning, like the world changes. So pre-deep learning, classical 3D reconstruction, you take multiple views of a scene, and you run a key point detector like SIFT or so, and then you establish correspondences based on the appearance patch around the key point, and these correspondences tell you a displacement between the points, and this displacement tell you something about the camera positions and about the 3D structure of the scene, and you get a beautiful reconstruction like this one, for example. And you can then also meshify the reconstruction by connecting, for example, with Poisson the points, and then you get something a little bit sparse, but it looks pretty good. So these were all kind of undesigned pipelines. Also, people did novel view synthesis before deep learning as well, based on feature correspondences. If you can put in correspondence your input views, you can establish all kind of granular geometric transformation, like here, homography, and then you can specify an in-between transformation, warp the images and blend the pixel values, and you get something. So pre-deep learning, perhaps it's fair to say that there are many different approaches, but they're all kind of limited in the range of change of view that they can do. Typically, you stay kind of close to your input views. So what's the promise of deep learning? Which is actually more than a promise because it's being realized as we speak these days. First of all, you can do 3D reconstruction and novel view synthesis given a single view, because you can learn priors about the structure of objects of a particular category and use it. Also, you can get to semantic level reconstruction. So go beyond a mass of points and say that mass of points is a chair. And this blends nicely two things I always liked, which are recognition and reconstruction. In many deep learning models, the two are kind of one entity. Also, we can get to multi-view reconstruction without doing point correspondences, well, with the caveat that you need the camera parameters, which somebody has to give you, which is also elegant. And in terms of novel view synthesis, you can get really accurate novel view synthesis, rendering also views that are far from inputs. But the main promise of deep learning is that it's a lot of fun 3D deep learning. You get to combine geometry and deep learning. I love it, and I hope you will too. So there are two strands that I work on, 3D reconstruction and novel view synthesis, and I'm going to start from the novel view synthesis part. So I'm going to show you about 5 works that we've done recently in our group, trying to go through how they work. So novel view synthesis, classical, you get multiple views of this bunny, and you want to generate new views that you don't have at the beginning. And how does it work? You in the modern era, you can build various models, and the most popular modern model is NERF. And the way it works is that you have a camera, you shoot a ray towards the scene, you sample point along that ray, and then you ask your friend, MLP, multivariate perception, what's the color and the density of the scene at that point? Now you can accumulate color values along this ray, and that will generate the color of your pixel. If you shoot array at every pixel of you have an image, great. Of course, the little detail is I didn't tell you how to train the MLP. I mean, where does it come from? What is good about NERF is that you only need the images and the cameras. You don't need the 3D scene. You can just shoot a lot of points along rays, the black points here, and then ask your current model to draw the scene following these samples, and then you check if the color matches your training views. Typically, it doesn't. Then you can compute gradient descent backward and train your MLP. Everything I've shown you, including volumetric rendering, is differentiable. Actually, it's easily differentiable as opposed to other things where you need tricks. And a couple of years ago, this made a big splash where people could get this nice truck. So the bad news is that you need a lot of input views. Users don't always have all these input views. And also, you need to train a model for every new object that you come up with, which is going to computationally be very slow. So our team and other researchers as well have been interested, can we do NERF from one view? Can we take just that view and draw the chair from all the viewpoints? And well, the answer is yes, otherwise I would be standing here. And here is how one can do it. Well, we don't have the multiple views. So how do we guide the training of the radiance field? And we decided to go explicitly through a process of establishing a 3D reconstruction of the shape that provides a geometric scaffold that can condition the rendering process. So here is an overview of the model. We think of image synthesis as a generative process where at the beginning you estimate or sample out a shape out of a shape network, really a whole 3D voxel grid. And then you can pass this on to guide the estimation of the narrow radiance field, which is this appearance network, which then can draw the image. And this appearance network is also conditioned on an appearance code, which conditions the color and the textures of your class. And then together with the shape code, these two codes allow you to model the variability of an object category like a chair. And in fact, these are really class-level models. I want to stress this. You train them on a lot of chairs. Then they become chair-specific. That's where the priors come in, and that's why we can do better than pre-learning. And then at test time, you can just give it a single picture of a new chair, and then you can do differentiable rendering all the way through. And the question you're asking is, what are the shape codes and the appearance code that if I would put them into this model, would draw that one test image? You can optimize through this, and then once you have it, you have your NERF and you can draw any view you want. So here are a few components of this model. So at the beginning, we have this shape network, which basically maps an arbitrary shape code to a 3D shape. And you can train it fully supervised with 3D shapes, with weighted cross-entropy, some symmetry loss, some chairs at least. And you can also have a nice stabilizing loss where you project the shape into the images in a differentiable manner, projecting on the silhouette, and you can have a loss on the silhouette, which really helps. And now, how do you train the appearance network? You get this shape from the shape network, and you condition the appearance network on it, plus the classical inputs, the 3D position, like in normal NERF, the 3D direction that allows you to do specularities, and you put in the occupancy that comes from your shape network, and the appearance code we discussed before. So now, when you're training this, you train both the appearance and the shape network so that together they will produce the input image, and there's this colorful difference like in standard NERF. And what works particularly well that we investigated, especially in our work, is to not only train the appearance, not only train the networks and then at test time only optimize over the appearance code, but do something like in generative latent optimization where you train the two at the same time, overfit into a test image, which makes it work particularly well. So in fact, we get to this now on a test image. You receive the image, mask and camera parameters, and then at test time, you optimize over the shape code, but also a little bit of the shape network so that you can reproduce the silhouette that you were given. So you can render it and then do neural rendering past the silhouette. It's also possible to optimize over the camera parameters, but I'm going to skip it here. Now, it's fun to see what happens here if you try to optimize both the code and the model on the test image because it gets much tighter, as you can see here. And you can do an analog game on the appearance network. You receive this shape from your current interpretation of the shape code. And now, again, you optimize over the appearance code and the appearance network for that, went fast, for that test image. Then again, if you try to optimize both, you can get domain adaptation effects. Especially when the training and testing domain differ a lot, this really helps getting sharper results. So how do you render novel views? You are given a camera path. You sample rays on this camera. You sample points on each ray. and you ask your MLP to produce colors, and basically just standard nerf. The difficult part is training it. Here are some results on chipness SRN, which has the same domain as the training data. So here, these are really simple renderings, simple lighting, and from the single image of this car on the left, you can get any viewpoint, including views that show parts that are hidden, which shows the priors that have been learned by the model. And you can do the same for chair. Chairs is beautiful because you can find a fourth leg. You can never see all four legs from this side. But now, getting more interesting, this is kind of data we have seen in several papers. What is interesting is now trying to render at a higher level of accuracy, beyond what you have in the training data. Can we do things like higher resolution, more complex lighting, cell shadowing with the same model? And in fact, we demonstrate this generalization beyond the training domain because we managed to optimize both the latent codes and the network parameters. And you can push it further, and with the same model trained on ShipNet SRN, you can also go on real images. Well, here with the caveat that you have a perfect mask that has been granted to you. So this was the first piece. Now, another way to improving on NERF is to take it outside. Let's take it outside. So instead of doing NERF on simple indoor objects, can we do it in a scenario like on Street View, for example? And in fact, I'm at Google, so we have access to Street View data. That's good. Here, a Street View tracker travels around with a backpack, taking a full panorama every second or two. And it also has a LiDAR sensor that gives him 3D geometry at sparse positions, but very accurate when it works. So can we use this to do better than Street View? Currently, Street View is a bit of like traveling on rail of a train. You can move the camera, but only along the acquisition path, and only jumping from an acquisition point to the other. Can we instead make it so that you can move the camera arbitrarily? And if you want to do that, you need to extend NERF to cover a few things that are annoying you. The auto exposure problem of the cameras, we'll look at it soon. Model the sky, which doesn't have density, unless an airplane is passing. And use the LiDAR supervision. So LiDAR supervision is good because you know some facts about the world. You know that there is high density near the LiDAR point, zero density before the LiDAR point, and you don't know exactly what happens after a LiDAR point. So you can now put this all into your losses. You can say, well, the LiDAR shoots a ray to the scene, and near the point where the ray ends, I should have an increase in density predicted by the model. And you can put this into your loss. You can say, well, before that point, please don't put any density. And after that point, whatever. And on average, try to put your average density mass exactly on the point. So that allows you to put it during training the LiDAR, and then you can forget it at test time, you can draw any view. So a big nasty problem is that trackers don't care about machine learning or computer vision. They go around with auto exposure. So what happens is that as the sunlight changes or you go around the corner of a house, the same physical structure appears with different colors. So that's very annoying, but the way we solved it is to model an approximation of the physics of auto exposure and estimate a global affine color transformation for the whole scene. For every single camera, separate affine color transformation, which will compensate the colors and map them into a common space. So another thing annoying about NERF is that if you shoot a ray to the sky, there is no density, but NERF absolutely wants to give it a color, and it can't, because it needs density. So it starts to put clouds in the middle, just so that it manages to produce blue. So instead, if we can detect with a segmentation model where the sky is, and then we gate the neural network to pass through a separate MLP that is only parameterized by orientation and not by position in 3D, and it's basically saying, in this direction, the sky has a certain color. So then you can estimate that, and you don't have artifacts. So we tried this on a lot of cities, in many continents. This is supposed to be a comparison. If you start from a state-of-the-art NERF implementation, MIP NERF, it's a bit blurry on this data. Wow, that's low resolution. If you compensate for exposure and sky, it gets a lot better already. And if you add LiDAR, it gets better, especially at the distance, when the depth is far away and it's difficult without it. Here you can see a video, or you will see a video. Notice how perfectly we render the weight icon. That's also NERF. Most expensive render icon ever. Hello. OK, let's try the next slide, and then we go back. I try next. Let's try next. Does this play? Woo! Now it's gone. It's very gone. Oh, this one plays. Well, this one shows both points. Let's not even go back. This shows you that we can render new views far from the acquisition path. The blue line is where the tracker went, and the red dot you saw move is a new camera that, maybe play this one again, is the new camera. Well, okay, I just go next. Oops. Wow. Techie. Let's scroll down to, let's scroll a bit more. Scroll, scroll, scroll more. But the video was cool. I was ahead on my time, just for the record. I have here all my timers. And I was finishing in 35 minutes. I promise you, I have every part of my talk written down. Okay, so anyway, you saw this one. Let's look at the next one. Look, it even works. That's beautiful city of Zurich, my hometown. And again, look at the red dot. We can be really far from the acquisition path, and yet it works, which is really a better experience than Street View offers today, thanks to NERF. So you can also get geometry out of this, depth estimation. Here is an input view. State-of-the-art NERF works, produces some depth, a bit blurry, because it's confused by the changing in the exposure and by the sky. But it gets much sharper by compensating for those two. And again, the distant points get even better thanks to the LiDAR. You might say, why don't you just do LiDAR? So this is the best we could do with LiDAR by splatting it densely, depth-aware splatting, a lot of tricks. The problem is that it has a very weird scanning pattern and often misses pieces. So it's a useful signal, but alone it will not get you the full reconstruction. Here's another video which for sure will play. Look at this. And you can see a dense depth map produced by such a method. Again, you can change your viewpoint. And from this, you can get to a full 3D reconstruction like looking here. This is not Pompeii, although it looks like these are actually different cities that are rendered Pompeii style by stripping off the texture. You can also take this geometry you estimated and put it into a mesh, which is much, much easier to render. It doesn't take you seconds per view, it takes you milliseconds, and you can render it on your browser, but it doesn't look as pretty and it doesn't do specularities. So I am still on time. I'm now going to move on to some works on 3D reconstruction. This is something we did a couple of years back. So the task here is you are given a single image with multiple objects, and you should do simultaneous recognition and reconstruction. You should get every object out with their class label, their 3D shape, also reconstructing the missing part like the mag angle that's missing there. And you want to get all the objects into a globally consistent coordinate frame in 3D without self-intersections. And the rough summary of related work is that there are 100+ papers on handling the case of a single object, and only a handful, maybe 10 or so, and in the case of multiple objects, including some by George. And the way we did this is in a single unified big model, and which merges two popular representations, voxel-based methods that have been used a lot for single object. They're nice, but they require a lot of memory, typically cubic in the resolution you want. But what they have nice is that they are translation equivariant, which means if you move your object in 3D space, the signal response moves along with it. Occupancy networks, or implicit functions, are even more popular recently. They are good because with a fixed memory footprint, you can get arbitrary resolution in theory, but they are not necessarily translation equivariant. You don't quite know what they do behind. And you need to repeat inference, maybe not for every point, but at least for every batch you send to your GPU. So we try to fuse these two and get the advantages of both, get high resolution with fixed memory footprint. And we start from a standard voxel grid encoder-decoder, which takes an image, pass it through an encoder-decoder, and it predicts occupancy on a 3D voxel grid. So now the very, very small intellectual jump is to say, no, that's not a voxel grid. It's a 3D grid of points, which are offset from the origin of the coordinate system by a parameterizable offset. So now you the user takes, please shift the whole grid by a certain delta, you condition the 3D decoder on it, and boom, you can generate grid of points at arbitrary points. Of course, then at test time, you pay the price that you need to run inference at multiple grid offsets, and then integrate everything to get your high resolution and also training time. Then at the end, you can get meshes if you want. So this gets the best of both worlds, because like convolutional voxel models, they have translation equivalence, but like implicit functions, we can get high resolution with a fixed memory footprint. And this is really important in multiple object scenes because the objects are small, so you need a lot of resolution. And the second thing we did it to make it work well is ray trace skip connections, which the idea here is to reconstruct in camera space and assume that we know the camera intrinsics, which often you find in your EXIF tags. And then, if you know these things now, we can start shooting rays that start from a pixel and cast frusta, maybe next slide is better, they cast frusta into 3D. So this way we can connect a pixel with this feature in the encoder layer to a whole frusta in 3D into the decoder layer. So now we can establish exactly the right correspondence as opposed to normal skip connections. And these carry local detailed image information into the 3D space in a physically correct manner. And this really helps getting sharp results. Now, this was valid also for the single object case. And if you are in the multiple object case, you can simply make the model predict a multinomial distribution over all your classes instead of a binary value. And then you can do lots of clever post-processing to get your, to disentangle the objects by thresholding the high resolution grid. Because everything is into one grid, you cannot have the case where two objects occupy the same space. You can just threshold the probability as 0.5 and you're guaranteed to have no self-intersections. So in the end, you get all the objects in a single coordinate frame because it's one model, and they never intersect each other. And these elements I told you, they're useful in general, but when you have multiple objects, translation equivariance become really important because the objects can be anywhere in space, so you want the signal to follow. And because they occupy a small fraction of the scene value, and you need a resolution. And the ray trace skip connection, the paper we validate this a lot. They are especially helpful when objects are occluding each other because they propagate occlusion points and help you understand the depth relations. And we have various experiments on single objects. You can see you can get the back of the chairs or the back of the car, which again shows the role of priors. You can do wiry structures thanks to the ray trace skip connections and the high resolution. And more important scientifically, this mix of voxels that occupancy network actually outperforms both. You can also do it on real images, on Pix3D, but more important, you can do it with many objects. Now you can have multiple objects occluding each other, and the model can hallucinate the parts of the objects that are occluded by another. This is especially easy to look in a zoom with this handle of the mag that's reconstructed. And then if you put a camera under the table, so that's unusual, but it's useful. If you put a camera under the table looking up or above looking down, you get a map. And this map gets you a sense of this coherence, of this all the relative spatial relation being preserved. Here is another example with this couch. The cusp of the couch is reconstructed again, thanks to the priors. So anyway, this is it's good, but it also has disadvantages because simple end-to-end training is very good. You get this coherency embedded in, but also if you train things this way, you are baking very subtle knowledge that's difficult to see right away that's baked into the model, like how exactly are the class combinations, how many objects there are in the scenes. And in the end, this is simple and very high performance, but it's difficult to scale it to arbitrary number of objects, like 50 or 60, because it tends to replicate what it trained. This brings me to the video part of this talk, where we're going to try to do something similar, but this time on real videos. So here is this video, which plays, surprisingly. There is this nice bedroom from ScanNet, and the objective is, and you have the cameras always, you always have the cameras in every part of my talk. And the objective is to output 3D reconstruction of all the objects, a variable number, a high number. And the reconstruction takes the form of CAD models that you take from a library, and you rotate them around in 9 degrees of freedom, so 3 translation scales and 3 rotations, and you put them all into a single giant coordinate frame that's coherent for the scene. And the way we are going to do this is we are going to leverage state-of-the-art methods that operate on single frame, like here Master-CAD, but could have been Measure CNN or others, Masker CNN. And these methods will produce some approximate localization and some degree of pose estimation, maybe not perfect, but good already. And we are going to fetch a model from the database, and then the contribution is to integrate all these partial pose estimates into a single coherent output on the right by doing multi-view optimization. And here is a bit more details. In this case, we use the Mastocad model for single frame predictions. A normal 2D model would output you a bounding box, a class and a score for every object, and a mask. Mastocad in particular also outputs a 2D prediction of where the 3D box center is, the 3D object center, I should say, which is not exactly on the 2D spot in case of occlusion and truncation, and also an estimate of the 3D rotation and a shape embedding that allows you to fetch a CAD model for a database. But this for particular work is going to need the object scale in 3D and its depth from the camera, because there is a big problem with scale depth ambiguities. Giorgio was talking more about depth and focal length ambiguity, but it's threefold. If you know the scale of the object, the depth, and the focal length, all three are entangled. So you can resolve for that ambiguity with video. That's one way to do it. And you can also improve all the other pose parameters. So we do tracking over time, and then we take these partial estimates, and we put them all into one global optimization objectives that say, OK, find the 3D rotation, 3D scale, and 3D translation so that your rotation objective can just simply say L2 norm on, try to fit the rotations predicted in individual frames. And then the fun starts with the translation objectives, because you can say, well, the 2D projection of the hypothesized 3D center should match exactly the predictions. And this means you're putting depth into the equation, the betas. And because you can cheat, in one image you can cheat, you can make the object bigger and farther, and it reprojects to the same point, but with two images, you can't quite do that. It would mismatch. Also, you can get scale out of the fact that the whole polygon mesh should reproject covering the bounding box that were detected. That gives you an idea of size. You can also get scale by recognition. So this is all scaled by good old school multi-view geometry. But you can also get scale through recognition. By enhancing these single frame models, you can say, well, I know it's a chair, so it has a certain distribution of sizes. You can train these models to predict object size. And once you have object size and their intrinsic parameters, you can flip it around to get depth. And that's also something that we put into the system. It's not very accurate, but it's better than not having it. So in the end, doing multi-view integration, we solve the scale depth ambiguity, we'll improve all pose parameters, and we resolve occlusions and objects that are out of view in one image. So here are some qualitative results on this dataset ScanNet, Scan2CAD. On the left, you can see the best we could do with a single frame baseline. So we took Mass2CAD, and we put it on steroids. We gave it this scale depth prediction from a frame, and we also take care of no-maximal suppression by removing duplicates that happen between different frames. Yeah, just about asking nicely. So here is an example of a scene with really, really many objects. And it's, a monolithic model will have trouble here, but this model works well. Here is a case where even the single frame baseline gets the structure roughly right, but it's not geometrically as accurate as doing multi-view integration. Concretely, you find a lot of experiments in the paper, but compared to the best we could engineer from a single frame, it's almost 3 times better. And it also outperforms other works that take video. You can look at top-down maps of this. This really gets, I'm a bit obsessed with global coherence and common coordinate frames. I find that a real proof that it works. So we often draw these bottom-up or top-down maps, and you can see that you can get multiple objects in the right spatial arrangement this way. And on top, you see those frames are reprojections of the input frames with reprojected CAD models. Something can be quite messy. I didn't make the dataset, but that actually makes it hard to look for a human, but particularly interesting for a machine. There's a lot of replicated objects that make it difficult to associate across views. Here, there are actually 2 tables in this scene. And the model has to distinguish them and reconstruct them as 2 separate tables. There are many works on this data that benefit from RGBD sensors, so structured light like Kinect. Thanks to that, you can get a dense point cloud, and then you can fit your CAD model straight to that. And of course, it works well, almost better, actually a bit better than from video. But then, you're stuck to those videos. Instead, if you can access a broader range of videos, let's say every video of an apartment on YouTube, you can start to open the door to other applications. So one thing we extended this model to do is to take also manual annotations in a few frames, like 2 or 3 frames per object, a few key point clicks, and then the rest we push it through multi-view optimizer to get 3D alignments. And if you do that, you can get to reconstructions that are almost perfect with very little human effort. And the ground truth in this case is done by manually fitting models to RGBD scans. So we are producing a very large data set, like hundreds of thousands of objects on real estate, real estate in the sense that they are apartments that people had for sale. Why did the video stop? I don't know, but and they're really pretty, much prettier than a ScanNet and much more varied. There are also exterior scenes, and we hope to release this maybe on time by Christmas or a bit earlier. And then we will finally have dense supervision at the object level on real data, not synthetic, in a variety of environments that I think it's useful. So I go to my next work, which is Raytran. Basically, it's the same task we saw before. So you have a video and you want to produce a coherent 3D reconstruction for all objects, but we want to obsolete the work I just showed you and all its companions that were similar, because all that series of works, they're all based on this concept of there is an image, you detect an object, you try to do partial pose from it, track it over time, multi-view optimization. It's a very systemic thing. Tracking by detection is super painful. I don't recommend anyone to try to do that by hand. Download a library. It looks great maybe when Alex does it, but if I try, it takes months of engineering. And then you cannot train end-to-end the system because, how do you propagate through it? So now we try to wipe it all clean, build a single unified neural network which will do no tracking and no 2D detection. It will do some detection in 3D, that's important, but no tracking, no 2D detection, and you can do end-to-end training with it. So I try to give the gist of this model. So as input, you have your video frames with your camera poses always, and as output, you have this. You want to get a class, a shape, and a 3D pose for every object. And the key idea here is to maintain two representations in parallel. One 2D representation that looks at the scene from the perspective of one view. It's basically a 2D feature map, like from ResNet. And the other one is a 3D representation that tries to describe the whole volume globally. And we can initialize this by shooting rays out of the pixels and aggregate features in one of these grid cells as they pass by. So if two rays cross, both features will fall into that grid volume, and also all the things around the ray. So it's going to be very blurry at the beginning. Then the new idea comes is to have a progressive exchange of information between these two representations that is done with transformer blocks. And gradually, as you do cross-attention between the 3D representation and the 2D ones, you get to a point where at the end, you get a 3D feature grid, which has a global representation of the scene volume. It aggregates information from all the views, taking into account all the context. And one feature vector inside one of these will contain an aggregated information content from all the views that see that piece of 3D volume. And that's without doing any tracking. That's really the interesting part. And then, of course, you want to detect objects in an arbitrary number. You don't want to be too monolithic. So here you can add a 3D det. Det is one of the most popular detectors these days. And you can train it fully supervised to output 3D pose, class, and shape, but inputting this 3D feature grid. Then you can make it train better, but also adding a few tricks, like predict classless occupancy and reprojected segmentation masks is not so important. So now this sounds good. The power of transformers into a 5-dimensional space. Who says it's a bad idea? It is, because good luck running that. Good luck fitting it into memory. That's a lot of pairs. If every pixel interacts with every voxel, you have a little equation below. Image height, image width, volume, frames. For us, it was like 50 gigabytes for one video. We couldn't fit it on a GPU. So our contribution is to sparsify this. In practice, you don't need all pairs of voxel pixels to really transform each other. Typically, it's more likely for a pixel to affect a voxel if it is on the projection ray, the camera ray that connects the voxel to that pixel. So you can compute them all because you have the camera matrices. And now you can sparsify. You can see the values are already quite low out of that part. And they get to 0 if you sparsify. And then you get basically a quadratic speed up. You go down as if the voxel cube was just one dimension. And it gets feasible, and you can train this. Here is a video which plays with a reconstruction of a long scene from ScanNet. You can see through walls because the model doesn't know about walls. Not because it's very smart, it saw a view from inside the bathroom before. In this case, it produces a voxel grid like a CAD model, so it looks a bit dirtier, but it's also sharper, more closely on the objects. And maybe I'll show you another scene. This is the scene we had before for Vit2CAD. You can see now how this model also solves it without the need for 2D detection or tracking. You can see my beloved top view map that gives you a sense of the structure of the scene. On the right, you get the ground truths, again, from ScanNet. You can see there can be multiple objects. They can be in complex spatial arrangements. They can be in chaotic spatial arrangements. Sometimes you wonder how good the ground truth is. There is a yellow-orange bin that we reconstructed, but it's not in the ground truth. And quantitatively, these results are even better than the previous paper I've shown you. And to my knowledge, these are the best results on ScanNet, given pure RGB. Maybe I'm too fan of my top view maps. Here are 3 more. So with this architecture, you can do even more than 3D reconstruction. You can try, I always felt, why is NERF so good at new view and okay at geometry, and these models are so good at geometry, but man, they cannot do new view. Can you try to go towards unification? This is a small, humble attempt. With the same architecture, you can chop it off at the feature grid, and now you can take the camera parameters for a new view, right? You can initialize an empty pretend feature map. Imagine your ResNet outputted some random values. Well, in reality, we have a default average view. Now you can start to do cross-attention, which in this case becomes a projector operator that takes the 3D feature grid and projects it into that camera parameter view. Then you get this sort of fake ResNet output, the yellow bit there. Then you can upsample and decode it into a real image. And you can train this all end-to-end by omitting views. You take one of your frames of the video, you pretend it's a test image, you can train the whole thing. And then it produces results that are not as clean as NERF, but they do something. And you can show, for me, this is an important proof of intelligence. If you look at the result there, the 2 closest input views are quite far from that view. So to be able to do this, you need some degree of 3D understanding. You cannot just try to homography around or move just things by a small amount. You really need to have understood the scene. This ends my technical core part, and I'm still on time. With my remaining minutes, I will talk a little bit about future work or what I hope the community would invest into. What I really like is the idea of general editability. So we saw in NERF we were changing camera viewpoints. You can also change lighting these days. NERF is particularly good because it's so good at drawing. Many of the models I show you later are good at reconstruction, but not so good at drawing. But can we get these models to be good at drawing with a level of 3D understanding that would allow them to do much more modification than just changing viewpoints or lights? So can you add an object to a scene, like this rubber duck? I hope it comes out better when you guys solve it, because that rubber duck is really photometrically so wrong. Can you remove the chair and fill in the background in a way that's photometrically accurate? You cast shadows, reflections right, filling in the mirror behind. Can we add a text to a chair, change texture, change its pose a little bit? Can we do this all from one image? Well, of course, the community is clever, and several papers have appeared recently that try to push the boundary of NERF, but they all have some limitation. Edit NERF, for example, has a similar model to our Sharp with latent codes, and it allows you to edit a bit of the texture, but then you can only do one object. And 2 recent works managed to change the position of objects, but only the position, only locally, and they don't do the cross shadows right. They cannot remove objects. They're still getting there. But if we really study these works, we get to my main message. We can see that the limitations of what they can edit is a reflection of the level of 3D scene understanding that's inside the models. And to do better, we will need to get stronger and stronger scene understanding to be able to do really general edits, especially from a single image. And the more sophisticated the edits you want, the stronger the required understanding, and the more you reveal the failures of existing models. So for me, the ability to edit a scene, especially from one view, add an object in the distance with all the shadows right, it's a sign of intelligence, of having understood. So I will end the talk on a bold quotation from Feynman. So what I cannot create, I don't understand. I think it applies here too. Thanks for your attention.